Okay, so welcome everyone. We're going to give you a presentation about artificial curiosity. We'll be introducing the concept of curiosity in reinforcement learning. So just to start off, we'll be three employees of Visium presenting this workshop. So we'll have Thibault here, who will be taking care of the coding part. We have Gaëtan in the back, who's our Windows guru, because you already have problems on Windows, and myself, who will be presenting the theoretical part about this presentation. So first off, I'll assume that you all know about machine learning. There are three main areas in machine learning. You have unsupervised learning, in which you don't have any labels to your data. You have supervised learning, during which you have labels for your data. And finally, reinforcement learning, that we're going to talk about now. So, reinforcement learning is actually quite easy to understand the idea. Can you talk like this? No, not really. It's a show. Okay, so you have, in reinforcement learning, you have an environment and an agent. The agent is going to be the intelligent part of your concept. So the agent, being in this environment, will be in a specific state. Based on this state, it's going to take an action. And this action will have repercussions on the next state. So it's actually a loop that is going to be going round and round in this environment. And sometimes the agent will receive a specific reward for this action that will allow him to know, is he doing something good or bad? And actually, to be sure that the agent is learning something, the goal of this agent is actually to select the actions that will maximize the cumulative rewards. So you really need to see this as an agent who's really trying by trial and error, like a little baby who's trying things and getting punished if he does something bad, and getting rewarded if he does something good. So a little bit of explanations. So this is going to be useful for later on when we go a bit deeper into the code. So you have the term episode, which is actually the sequence of states observed, the actions taken, and the rewards received. This is important because during the training, your agent will have multiple lives. He's going to try something out, lose or win, and then try it again and again and again. And you need this history so it can learn from these episodes. Then you have the policy, which you can actually see as the decisions that the agent will make. So the strategy that he's going to take. What is it's going to be a function that will map the next best action for the state that he's in right now. Then you have the discounted return. So in reinforcement learning, you will have rewards.
Just one last thing.
Great. So you have the discounted return. This is actually going to give the sum of the future rewards received after each step until the episode ends. The idea here is to have an idea of a representation of how much reward the agent can get in the future. And this is highly linked to the value function, which is the expected discounted return from a state from following a given policy. So the idea here is to say, is the reward more important on the short term than on the long term? And these two functions is going to allow us to take into account the really long-term rewards that the AI could get. So, example with Mario. In this situation, you will have here Mario is the agent. The environment in which he evolves is the game. When he does something, so the action that he's going to take is, for example, going to the right, jumping, going to the left, or sending fireballs when he has a power-up. And these will bring him in the next state. The next state, for example, in this situation, he has been throwing fireballs. This fireball actually killed this enemy, and he receives a score for this. So he can know, is this good or bad? In the situation of Super Mario, it's a really known game for reinforcement learning. And in this situation, actually, the reward function is really complex. So for example, when it goes to the right, it will get points. And it goes to the left, it's not going to get any points. The idea here is to put the agent in a situation that he's going to be able to learn. And now you're going to code your first agent.
So, hello everybody. So just to get an idea, because you're really many people, so raise your hand if you could install Docker and everything. Okay, great. If you haven't, try someone next to you who did. it should not be that hard to do. And otherwise, you can go on this website where you can see the address. So this website, there's a link on the README of the GitHub repository. This website will allow you to see the code, the solutions to the coding exercises, and will allow you to visualize the agents, but it will not be interactive, so you cannot modify the code if you go to this website. If you have Docker, you can just run the image you just built and go to the Jupyter Notebook server that was started when running the image. So you go to your local host, type the token, and you should enter the source directory of the repository where all the code lies. Just once again to get an idea of who's here, who has experience with reinforcement learning? Okay. So for those who have more experience in reinforcement learning, you can dive into the code, those .py files, and if you know Python, you could modify these files and try to build your own agents. For the majority of the people, you can just open this artificial curiosity file, this artificial curiosity notebook, where most of the environment and util functions have been pre-implemented for you so that you can run your agent without having to know too much about Python and reinforcement learning. So let's start by importing all the dependencies we will need to run our agents. Just run the first cell. So we will use PyTorch for the neural networks in our deep reinforcement learning agents. We have prepared some environments for you. These are games that you will play today. And we also have prepared some neural network architectures and some util functions. So to get an idea of what we're going to see today, you can just print the supported environment that we have in our repository. So we have two Atari games, which are classic reinforcement learning tasks, so Pong and Breakout, and we have two different levels of Super Mario Bros. The next thing we're going to do is build these different environments using this make environment function and build recorders objects. These recorders have been pre-implemented for you to capture what the agent is doing in the game when you play it, and then you can replay the recorder to watch what your agent did. Okay, is everybody okay? Raise your hand if you're okay. Okay, so we can go to the next step, which is actually building the agent. Remember this loop? Well, we have our environment. It has been pre-implemented. But now we need the agent. So we will create this dumb baseline for our exercise, which is a random agent. A random agent has a uniform policy. So when in a game you have the choice between two different actions, a random agent will assign 50% probability to each of these actions and do one at random. So it won't learn anything, but it's a baseline to see how difficult a game is. So your first task will be to complete these functions. The idea is that your agent has a play function, which takes as argument an environment. So the environment we want our agent to interact with. You can specify a maximum number of games or steps for the interaction to last. And you can pass a recorder to your random agent to record what it does. Is it better now for those in the back? Yeah. So yeah, as I said, we have this play function, which is a unique function of our random agent. The first thing we're going to do when we play a game is just reset the environment, and then we are going to log some information. So every time we play a game, we are going to store which game it was it the first one we played, the second one we played, etc. The total reward we get during the game, and we will also increment a timer to see how long our games are lasting. So this is just for logging purposes and see what's inside your agent. The most interesting part of the agent is this while loop. So as Axel said, you have this loop of interactions between your agent and your environment, and this corresponds to this while loop in the code. So remember that at each time step, we observe the environment, so we get a state, an observation, and we need to give an action to the environment, take an action. And as a feedback, we'll get the new observation and a reward. So using this information, try to find what should be the output of this function here, and what should be the input and the outputs of this new function here. Ideally, you should get the name of the variables right just by looking at how the code is built, but the idea here is just to really understand this loop of interaction, so you can just pseudocode and get an idea of what you should give as input and what you should get as output in this interaction loop. So you can just take a few seconds to think about it, and yeah. Let's go. So, has anybody any idea of what this environment action space sample function should return? What should be an action? Yeah. So this function is this function sample. It's pre-implemented in this environment object that we created. Actually, we are using OpenAI Gym interface. So if you have already worked with reinforcement learning, it's a pretty standard framework for developing environments. So this environment.actionspace.sample function will take your environment, take its action space, that is the set of different actions that you can perform in this environment, and sample a random one from it. So you will get, as a result of this function, the action that your agent is choosing to do. Then the environment step function, it's another standard function from the OpenAI Gym framework. It's the actual action, function we call to tell to the environment, okay, I need to take that action, give me feedback. So what should be the input to this function? Yeah, so it's the action we just selected. It's how we tell the environment that we should take this particular action, and the environment should update accordingly. So what would be the outputs, what the environment is giving us back once we told him, I want to do that action? Do you have any idea? From this loop, you can understand that, we are getting back the new state of our environment. So in our code, we will call it observation. The state of the environment has changed because of what we did. So we're getting an update on that. What would be the second output, the second feedback we get? Yeah, the reward. So basically after this action, we're getting a feedback from the environment telling us, yeah, this is something good, or no, this is something bad. And in the context of this workshop, we will call the reward Extrinsic Reward. We call it Extrinsic Reward because this reward does not come from the agent itself. It comes from the environment. It's an extrinsic motivation. And we will see later when we will make our agent curious that agents can also have intrinsic motivation. Now, the tricky part maybe, but if you looked at the code carefully, you could have guessed what this is. What is the third output we get from our environment? The third feedback. We get this reward, this new observation, but we also need a new information. Exactly, is game over. So basically, if you remember the notion of episode, this succession of state actions and reward that we get, an episode here would be an entire game, from the start of the game to the moment where we win or lose the game. So we need to have that information. does the action I just did end the game or not? Once this interaction with the environment is done, we update the infos we want to log about what we just did. And this is why I said if you looked carefully at the code, you can have guessed the different outputs. We have a particular case. If the game is over, we increment the number of games we have played and reset the environment to play a new episode, a new game. So normally, you should be able to execute this cell and the two next ones. So the two next cells will build an instance of this random agent and ask it to play Pong, which is our Pong environment, for a maximum of 1 game or 500 steps. If you are confident that your computer can run this fast, you can increase these numbers to make it run for longer. But anyway, it's a random agent, so it won't really change through time what it does. Once this is done, you have passed the recorder to your play function, so you can replay this recorder to display an animation of what your agent just did. So this is the Pong environment. We are controlling the green bar, and we have 3 possible actions: doing nothing, going up, or going down. So at every step, you generate a random number between 0, 1, and 2, and you send to the environment the information that you want to do that step. The problem is that we are acting randomly, we are not learning anything from the rewards we get back, so we are just missing the ball every time. So this was our random agent. You can try to run a random agent in any of the pre-implemented environments we provided you. So remember that we have these 4 different environments. So if you want to play a little with different games, you can type breakout instead of Pong, rerun the cell, and you will see how your random agent is performing in breakout. Breakout is really similar to Pong, except you don't have an adversary, you have just this wall of bricks. You can go left, right, or do nothing, and the goal is to break the wall of bricks above you. Finally, let's start with a more complicated game. So we will run Mario level 1. Just to see what a random agent can do in that environment. The interactions with the Mario environment are slightly slower than with the Atari environments, by the way, so just be patient when you run it. So it's not really good. Half of the time, Mario is going left. That's already a bad sign, because we have this random policy, and the different actions we can take are combinations of pressing buttons on the game controller. So we can go up, down, left, right, press A, press B, and combine these buttons. So in many cases, the actions are doing nothing or going left. So sometimes Mario kills an enemy, but it's just by accident. So now that we have the worst Mario player in the world, we can try to make it smarter using reinforcement learning. So Axel will now speak a little bit more about reinforcement learning and how to make this agent play Mario better.
Thank you, Thibault. So you saw this example with Mario, with Pong, with Breakout. These are really basic games. But if we want to apply reinforcement learning to more complex tasks, we need to consider more complex environments. And actually, StarCraft is a really complex environment. For those who follow a bit reinforcement learning, this was a victory of DeepMind's reinforcement learning agent called Alpha Star on one of the top human players. And actually what happened was that one of the key factors for the victory, as the commenters said, was the fact that the machine was able to control way more and more precisely all the different units. And you might be thinking, oh, these guys, they want to play video games all day. You need to consider that actually in this situation, the potential actions. So for example, in Mario, it was 16 potential actions that Mario could take. In this one, it's over 1,000. And you also have the victory of Go from DeepMind's team. The AI was called AlphaGo. And in this situation, it was also the same. It was something that was considered really hard, and using reinforcement learning, it was possible to train a model to really beat human capabilities. But don't be too sad. What happened in the AlphaGo match was that one of the plays that the AI took was actually something that was never seen before and really surprised the human player. But what was really interesting is that after that, the human took the same action and was able to beat the machine by playing it at his own game. And this is something to consider. You're not all doomed, you're going to learn from these machines, and that's really important. So now, a small exercise where you can discuss between each of you for 5 or 10 minutes potential applications to reinforcement learning. So what we need you to think is what would be the agent, what would be the reward, and what is the end goal of that reward. So for example, in the case of stock optimization, your agent is going to take decisions to buy or sell and taking the information from the environment. So having all the information that can be found on the web, for example, and the reward would be, for example, the gain or the loss of money. So maybe try to create groups of 5, 10 people, discuss with people around you, give you 10 minutes, try to find something, and then we'll do a small round of potential application that you thought about. Of a potential application. Or I can just ask someone directly. So maybe you.
Poker, maybe?
Sorry?
Poker.
Poker. Okay, so what would be the agent? What would be the reward? How would you maximize the strategy?
Like value in chips, whatever you have. Environment would be the cards you have on your hand and other players. Would be also information like which cards are shown, how many cards are shown, as well as the cost. Actions are the classic ones, so there's like raise, call, pass,
I would say in this situation, how would reinforcement learning be more interesting than other machine learning techniques, for example? Maybe I'll just say it out loud. So the application is poker. The agent would be just an agent playing the game. The potential actions are the usual games that you do, and the reward function, the rewards would be either if you win or lose the game, if I'm correct, Dominic? Yeah. And the question I was wondering about is how would this be more interesting, why would it be more interesting to use reinforcement learning than typical machine learning solutions? So the problem being, if I understand correctly, the lack of data, of labeled data. So, okay. So yeah, one of the problems would be that actually the strategy that the AI would choose would be, for example, something that he has already seen already. And in the case of reinforcement learning, since you give it a reward function, it's going to find the most optimal way to find a solution to a problem. Okay. Does someone else has an idea?
I'm not saying that's a good job.
Of application?
Like, is it normal?
Yeah, it's normal. But I mean, what else would you do? It's just playing around
So-
and...
What? Autonomous driving? Never heard of this.
So I guess I'm surprised you didn't just
Yeah, so autonomous driving is one of the big ones. Of course, you want to have an agent that is able to understand everything around it and optimize the path. And then you also have the big questions, ethical questions. For example, if you say to the car, the reward is to get from point A to B as fast as possible, maybe it would be nice if you also give a bad reward if it goes over pedestrians or something like that. This is something to keep in mind whenever you build a function. Okay, so we also have no. 1 moment. Here we go. Yeah. So here's another example. Autonomous flying. So in video games, you have the possibility to control everything, also in simulations. But actually what happens in real life, especially when you're flying, for example, a helicopter or a drone, the big problem is that it's chaotic. The environment is really chaotic and you can't just give him really easy tasks to do. So by building a reinforcement learning agent that is able to control this helicopter, you actually give this agent the ability to adapt to all the small modifications that may occur in that situation.
How would you give it the freedom to train? Because for Mario, if he falls down the pit, nobody cares. But here, if he falls down the pit, you care.
Well, it depends of how well you're funded. Now, in this situation, actually what they did is they did a simulation. So they had one of the a perfect professional helicopter pilot playing with a remote for this helicopter, and they actually modeled what he was doing perfectly. And then, and this was used standard supervised learning, and then they created a simulation in which the reinforcement learning agent could learn, and then it was replicated in real life. So, but it's a good question. Okay, and then, for example, there are other applications. First one, inducing app crashes for debugging. So I talked with a friend from cybersecurity. What people try to do is whenever you try to crash an app is you press multiple buttons at the same time, you try to open a lot of things at the same time, and it can be a bit erratic and you actually need a bit of creativity to perform all these tasks. And you could create a reinforcement learning agent that is sole purpose in life is to annoy as much as possible your developers and would try to crash the app constantly. And when it's able to do this, actually developers can pick up on the error and then apply a solution to that. Resource management, IT resources. When you have limited resources, of course, you need to optimize everything. Traffic light control. In this situation, what you want to maximize is the flow of cars, for example. Portfolio optimization, as we explained a little bit earlier, warehouse stock optimization, and you see actually this optimization idea coming a lot and a lot. Why is that? It's actually mainly because what reinforcement learning agents will do is try to find a solution to a problem that you have, a broad problem. And it's going to try this through trial and error. So in this situation, for example, for Mario, it's going to start randomly to play. After some time, the random actions will sometimes do something interesting, and the agent will pick up on that, and it's then going to reinforce that learning. And this can be applied to everything. So at the beginning, your agents will be really bad. For example, in the case of portfolio optimization, it's going to lose all your money or maybe make a lot of money. But in the end, it's going to learn from the mistakes or the wins that he does. And this is the interesting part, because it can come up with strategies that are actually never seen before, because it's able to try so many different things and really fast. And so, as I said, you have this learning phase, and this actually brings the trade-off question of exploration versus exploitation. So when you put an agent in a new environment, it's going to start to look for different things to do. So in our case, randomly, it's going to perform different actions. And actually what you want to do in this exploration phase is you want to learn what is good and bad in your actions. After some time, you will actually find yourself in the exploitation phase. So this exploitation phase is when you think you found the most optimal path for your objective, and based on that, you are going to repeat this policy over and over again. And this problem is actually a problem in the situation in which your reward is more important than the value. So value is long-term, reward is short-term. And it is a problem that also humans we have, addiction. So in this situation, what happens is if you have too much weight on your reward, if the short-term gains is too important for your agent, it's not going to be able to think about the end goal. And here we have an example in which the agent is actually trying to race other boats. So again, in a game, of course. And the agent is really good at turning to the left, as we can see. And actually what we're going to see is that it's going to start to get some rewards. So this is really interesting because he's really good at turning left and he really enjoys it. So he's going just to go round and round and get as much points as possible, getting the next hit. And this can have two origins. So the first one is that the reinforcement learning is too much biased towards exploitation. And actually the short-term reward is more important than the end goal. And this is actually something interesting because in this situation, the engineer has to think about a better function, reward function, sorry. And yeah, and the second part would be that it's possible that actually this short-term reward is more important than finishing the race. And this is the situation in which you need to really understand that building these reward functions is something really hard. In the case of Mario, for example, it's a problem that a lot of people have been trying to solve. Sorry. And actually, it's really interesting to apply this reinforcement learning to new environments. And there's also a second problem, which is the sparse reward problem. So you're going to see later with Thibault that in some games, rewards can be quite sparse. So for example, in the game of Pong, you lose 1 point whenever you lose the ball. But you get 1 point when you're able to put it in the others, in your adversary's corner. The problem with this is that the speed at which the agent can learn is really slow. And yeah, voilà, sorry. Yeah, so this sparse reward problem is also a problem to be considered because in real life, you don't have a reward every time. So for example, you want to go buy milk in a new grocery store, you're not going to get more and more points the closer you get to the milk. You have your goal, at the end is going to get the milk, and when you get it, you can maybe get the reward. You're going to have a shoot of dopamine because you found your milk. And solving this problem of the sparse reward is something really interesting to apply reinforcement learning to other environments. I'll now let Thibault help you build a more smarter agent.
Okay, so after building our first random agent, we're going to build a deep reinforcement learning agent using state-of-the-art algorithm, which is called the advantage actor critic. So just to refresh these ideas, remember we have episodes that are successions of states, actions, and rewards. We generate these episodes by following a policy, a function mapping the current state to a probability to do a given action. And we are trying to maximize our average discounted return. That is the sum of all future rewards your agent will be able to get until the end of an episode, so the end of a game. We are trying to maximize that. As Axel specified, we are not only trying to maximize the reward we're going to get at the next step, we are trying to maximize the reward we'll get in the long run. So if something has a bad consequence in the short term, but then in the long run, it will allow you to get more and more reward, you need an agent that is able to make that sacrifice. And to do that, we use this actor-critic architecture. So in your actor-critic agent, you have two components. It's a neural network with two heads, two types of output. That is, in this neural network is trained such that the two outputs are trained simultaneously. So your first network is an actor, and it will output the policy. So you have literally a neural network with one output unit for each of your action. You apply a softmax activation function on it, you get a probability distribution over your action space. So for each action, you will get the probability to do it, and when you want to select an action, you just simply sample from this policy created by the actor. But now we need to train the actor. And for that, we will use a critic. The critic, his role is to learn the value function. Is to learn, given the current state, what is, on average, the long-term reward that will be obtained when the actor is on the commands. So basically, it's evaluating the actor. It's telling the actor, well, when you're in this state, on average, you're getting that much reward in the future. So that the actor can know that sometimes it does stuff that have better consequences than on average. And it will try to maximize these actions. So basically, you're training the critic to learn the reward function, but from a long-term perspective in a given state. And you're training the actor to impress the critic and to generate more rewards than the critic said he would do. So you have this generalized policy iteration. So you evaluate your current policy by estimating a value function. And once you get a value for each different state, you can improve the policy by picking the action that will lead you to a state with a good value. So now we'll try to look into the code and understand how such systems are implemented. So yeah, you have in the notebook the architecture of this actor-critic agent. And the class is a little bit more complicated than the random one, obviously. There is no code for you to do right now. Just we'll go through the class and understand what's happening here. If you want to go deeper, you can look into the networks.py file, where you can see the implementation of the neural network. Here, everything is wrapped in the notebooks, and so when we initialize our agent, we will simply create a network, an optimizer, to learn the parameters of our actor and of our critic, and we create a memory data structure, which is here to store our experience. So basically, to train a neural network, you need data. And your data is your successions of state, actions, and reward. So as you would collect a data set in traditional supervised learning, here you need to collect a data set of experience. So that's why you will store in memory everything you do. Then we create this actor-critic network. You can look into the class actor-critic in the networks file, as I said. And the display function, we still have an environment, a maximum number of steps and games. But now we also have this train parameter. And we have a verbose parameter that will print you additional information and the recorder. So just as before, when we start to play a game, we are resetting the environment and reinitializing the variables that we want to log. And once again, the most interesting part is in this while loop, this main loop of interactions with the environment. So the way actor-critic works is by rollouts. You will execute a small sequence of steps, of actions, and you will use this small sequence basically as a batch to update your neural network parameters. So here we execute rollouts of 20 steps. So for 20 steps in a row, we will feed our observation to this actor-critic neural network and get as a result an estimation of the value of the state we are in. So this is the output of the critic. The log policy, so the logarithm of the output of the actor. We take the log for loss purposes. And if we sample from this policy, well, we get the action we want to take in the environment. So instead now of sampling from a uniform distribution, of selecting a random sample from the action space, we will now run a neural network to decide which action to run. And we will store this value, log policy, and action, basically our network output, in this memory of past experience. Then, as before, we run this step function. Remember that we send the action to the environment, and as a response, we get back a new observation, an extrinsic reward, and a signal telling us whether the game is over or not. Basically, the fourth output, info, is just containing additional information about the environment. And now a new difference with our random agent is that we will use this reward, this extrinsic reward, to modify the parameters of our neural network. So we store that in memory as well. We need it to learn. We update the infos. And when the game is over, as before, we log the infos and reset the environment. Also, we...
What is this function get reward?
Okay, so this function get reward, it's just applying a small modification on the original game reward. It's clipping the reward between -1 and 1. So basically, if you're ever getting a reward that is -10, it will be clipped to -1. And if you get a reward of, say, 1 million, it will be clipped to 1. We do that to keep our update in a reasonable range. You know that when you train a neural network, you need everything to be quite normalized and in a good range and avoid non-values and everything going wrong. So basically, your agent will do unpredictable stuff. So you're not really sure about the quantity of reward it will obtain during its interactions. You want to be safe and just clip that in a small range. Basically, what we are doing is every time we start a rollout, we also reset the memory. And once a rollout is done, so we stop the rollout either after 20 successive interactions or when the game is over. Once this is done, well, we can train on actor-critic network. So here, everything is wrapped, and you can still go in the network file to understand how the loss is mathematically computed. But basically, you would use all the information you have in your memory, the values you estimated, the actual rewards you got, the actions you selected, the probability your actor was assigning to these different actions. You're using all of that to update these parameters. And we will see with the visualization what's happening inside the network to understand it more without looking at too much math. So you can just execute this cell to build our actor-critic agent class. And we will start by running it. So execute the 3 next cells, run the smart agent. And we added this verbose parameter to log after each rollout information about the game we're currently playing. So you see that after 20 steps, that is the end of our first rollout, we get a reward of 0.9 until now in the first game. So we told the agent to execute a maximum of 3 games or 500 steps. So after 500 steps, it stops. The recorder is preparing an animation, and then you can watch it. Well, I hope you're not too disappointed, because we promised you an intelligent agent, and, well, it's not really better than the random one. And that's because we haven't trained it yet. So at initialization, obviously, all your neural networks are giving you random outputs. So you're pretty much giving a uniform distribution as an output of the actor, so you're still doing random actions, and your critic has basically no idea of which states are good and which states are bad. So let's try to train this agent. And this is the next cell. We still execute this play function, but now with the train parameter set to true. So here I will train the agent for a maximum of 1 million steps and 10 games. That's not a lot, but that's enough. So you can run this for 10 games only. If you want, you can run it for a little bit more. The more you train, the better the agent will get. So let's run that. And in the meantime, while it's training, let's look at what's happening inside our actor-critic network and try to really understand how an actor-critic architecture can learn how to get the most long-term reward. So we have these videos of agents we trained. So we are not using the advantage actor-critic you have in your code. We are using a slightly more evolved version called A3C. So you have a new A in the name of the algorithm. It's called asynchronous advantage actor-critic. So basically you're just parallelizing your training, and you have several versions of the environment running in parallel, different agents running in parallel, and they are all updating the same neural network. So it's just a way to make the training more efficient, but it's the same system. So on the left, you can see your environment. That's the Pong environment you just saw before. And we give an observation to our agent, the observation is actually the frames of the game, but pre-processed, so we normalize them, and we stack together 4 consecutive frames from the game. So has anybody an idea of how it helps to stack several frames and give only, instead of only the current frame of the game, we gave as input 4 consecutive frames? Do you have any idea why? Yeah. Yeah.
Trajectories?
Exactly. Trajectories. So for instance, yeah, let's see this frame. Just look at the frame on the left. Can anybody tell me, just from this image, if the ball is going left or going right? No. So to transmit to your agent this information about the direction of movement, you stack consecutive frames together. Then you feed this into a convolutional neural network to extract features about your observation of the world. And then you feed that to an LSTM network to build this internal state, this internal representation of, okay, this is the state I'm in. You basically just use deep learning to extract interesting features in your environment. You can see that here the ball is moving, the agents are moving, but the features we extract are not changing a lot, because actually most of the frame is the same. I mean, only the ball is moving and the agents, but most of the frame doesn't change from one step to another. And our convolutional neural network is just extracting, random features. But we see that after 500,000 training steps, our features are starting to change a little. So we are picking up, okay, when the ball is moving, it's an interesting information. And then you use this state, you feed him to an actor, which outputs the probability of each action. You can see in orange the action that is selected at each step. So you can see that at the beginning of training, your agent is still close to random. Yeah.
Are you using the images themselves that ask for, or are you using the differences between the images?
We are using the images, the actual images, but we normalize them through time as well. So we keep a running mean of what a frame is and subtract this running mean from all frames. Now, can anybody tell me why our value function here? Well, I'll just go a little bit back in the training when we were at no training. Yeah, you can see that the value, so how good are the states I'm visiting when following my current policy, these values are very close to 0. So there is no training, it's basically noise over 0, the output of our neural network. But after these 500,000 training steps, we see that the value is oscillating between -2 and -3. Has anybody an idea of why this is happening? Hmm? Exactly. Remember that the goal of the critic is to estimate how good the current agent is. The current agent is bad. The estimated value of all the future rewards it will get in the future, it's something negative, because usually in the future it gets negative rewards because it loses the ball. Now, these oscillations are quite interesting because if you look into the detail, you're actually predicting in how long you're going to lose the ball. So we're getting down, 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 and as soon as we lost the ball, okay, this negative reward is past us. So now in the future, we don't have this negative reward that contributes to our sum of future rewards anymore, so our value is going back up again. But yeah, every time we start a new step, the closer the ball gets to the agent, the smaller the value. Because the critic is saying, oh no, something bad will happen, something bad will happen, something bad will happen. And then something bad happens, the critic is reinitialized, and it tells it again, oh, something bad will happen, something bad will happen. But what's interesting is that we train this system in what could be seen as some sort of adversarial manner to train both networks at the same time. So basically the critic, you're trying to create this smooth version of your reward function, predict what the sum of the future rewards will be. So you can simply use your 20 steps of experience to train the critic. You have actually, for 20 consecutive examples, an example from the real environment of what your agent is generating as a reward. So you can use that as a target for your critic. Now for the policy, how do we know when we want to increase or decrease the probability of an action? Well, if we do an action, say the critic now learned that we are usually losing points. So the value is between -2 and -3. So if once, by accident, we catch the ball and send it back to the other side, to the opponent, we will get 0 reward. But the critic thought we would get a -1 reward at that moment. So the critic will be impressed. And how much you impress the critic is how much you increase the probability of the action you just took. So basically, if the critic thought it was getting a -1 reward and you get a 0, even though you get 0 reward, no feedback, you create a positive value to increment the probability of that action that made you catch the ball. So we can see as the agent is continued to be trained. See here, we receive no reward, but the value was estimated to -1. We expected a -1 reward at that moment, but we get none. So the action we just did, that was sending the ball back, the probability of that action will be increased. Is it clear for everybody? Okay. So I can just fast forward this, but you can see that, yeah, after quite some time, the agent is even able to get points. After 1.5 million steps, yeah.
I have a question. Will it be easier or simpler to model the rewards with a small positive value every time you hit the ball back and send it back, and a larger when you actually get a point?
Exactly, so that's what Axel mentioned with the sparse reward problem. It's a perfect example of sparse reward problem. You only get 1 point every time the ball disappears from one side or the other. But yes, there could be much more information in your reward function. Problem is, then you need to code it and program it yourself and implement all these conditions where you want to give a reward or not. And there can be a lot of different conditions. So yeah, it's possible, and we will see with Mario that for more complex environments, that's what you need to do, because a sparse reward function will not be enough to learn quickly. But for Pong, you will see that this is enough, actually. Even with this very sparse reward, I'll just fast forward it. Okay, after 3 million steps of training, notice how now our level is balanced with the opponent. We're getting almost the same score, and the value is around 0, because I mean we get a point almost as often as we lose a point, so often our value oscillates around 0. Yeah. Yeah, I don't know if you heard, but so he said that if you get a reward just for sending the ball back and not for making your opponent lose the ball, then you just learn to, send the ball back, but never actually winning the point and trying to trick your opponent. And yeah, you can see that you have to ask yourself many questions and imagine different scenarios and trajectories your agent might take when you're designing a reward function. So now we are playing the game perfectly right now. Our opponent is never able to make any point, and you can see that our value function is always increasing, because it's the opposite from the beginning. The critic is now not saying something bad will happen, something bad will happen. It's saying something good will happen, something good will happen. I'm close to the point of making a new point. And you can see that the features are variating a lot from one frame to another. So we are only paying attention to what's changing in the environment, that is the ball and the agent. Here is an example on breakout. So breakout again, these 3 actions going left, right, and after 11 million steps, so the training is a bit longer, we get a policy which is close to optimal. The network has not converged yet, but it already learned a very good behavior. Has anybody an idea of what the optimal policy, the optimal way to act in this environment is? There's a particular strategy you can use to get a lot of reward really quickly. So you see that we are still in a situation of sparse reward. We get 1 point every time we break a brick. But there's a way to break a lot of bricks very rapidly. Yeah, exactly. I see people doing like that. And you dig a tunnel and you send the ball inside the tunnel such that it bounces back and forth at the top of the screen. So, yeah, again, I'll just accelerate it, but it's training, yeah. And you will see, so you see that big spike in the value function? That's the moment where we are opening this tunnel. And now we get really high frequency reward. And now the value is decreasing with time. So, yeah. Here is an interesting frame as well. You see that drop in the value? Now look at the position of the ball. So we are about to lose, and the value function represents that really clearly. So it means that when you feed these frames of the games to your critic network, it will know that when the ball is at that position and the platform is at that position, usually we don't get any reward, so the value drops completely. So it's telling the actor what you're doing usually in this situation is really, really bad. Again, if by accident the agent is able to recover from that bad situation and get a positive reward while the critic was expecting a negative reward, it will create a big advantage and really increase that accidental action that saved us. So that's it. Maybe we can take a break. Maybe we can have a small break and a discussion if you have any questions, and just start again in 10 minutes to go to the core of the workshop. Stop providing reward to your agent. Make it curious and let it use intrinsic motivation to create its own notion of reward. Start again. Just while we wait for everybody to come back, I'll show you a video to refresh your memory about what's happening in our actor-critic network, but now on the Mario environment. So when we launched our smart Mario agent and saw that it was doing random stuff, it was because the network had not been trained yet, and this is what you can see here. So it's like for Pong or Breakout, your feature and states are not changing very much from one step to another. And you can see two major differences between the Mario environment and the environment we used before. The first one is regarding the policy. We don't have 3 different actions anymore. We have 11 different actions anymore. Yeah, actually 12 different actions. So this makes the optimal policy, the optimal strategy, much more difficult to learn. Because now instead of 3 output units for your actor, you have 12 output units. And so the policy is more difficult to learn because you have more possible actions. That's quite simple. The second big change is that we don't have a sparse reward anymore. Using a sparse reward with Mario, for instance, just giving +1 if Mario finishes the level, it would require a lot of training, because you would need to wait until, by accident, just by doing random stuff, Mario is able to finish the level, and then you would get just a +1. So you would need to do that a lot of time by accident to understand that it is the optimal behavior, and training would take ages. So what you need to do is carefully design a non-sparse reward function that is not only based on the score, but on other factors. So can you try to find ideas of what you could include in a reward function for playing Mario? Every time it gets points, yeah, the score, it's already a good base. But most of the time, you get 0 points. As for Pong or Breakout, you only get points when you kill enemies, or when you grab special power-ups, or in certain specific situations. what else could you use? Exactly. So the distance that you travel is an important information. Just going right, even if you don't catch any new points, is always better than going left in this Mario environment. So every time the location of your agent is more to the right compared to the previous state, you get a positive reward, and every time your agent went left, you get a negative reward. So you get this continuous feed of feedback, because at almost every time, at almost every step, you either went left or right. So you will always get a positive or negative reward at each step. When you look at the reward function, you can see that. And you can see that the agent is randomly going left and right, because you can see that this reward function is centered around 0. So yeah, that's most of the information we use in our reward function. We also include the number of coins that were received, and whether Mario is in a special state. Like for instance here, we can see that our agent grabbed a mushroom and got bigger. This information is included in the reward function. So you can see that the reward is going up at the moment where you take the mushroom. And yeah.
The effect of scaling the various elements of the reward different. So you can weigh or scale the different elements that you just mentioned, and the results differ. Is that a sensitive thing?
Yeah, so all the different components of the reward function need to be scaled. How much do I want to reward the points? How much do I want to reward the direction of movement? And yeah, you have to fine-tune that and find a good reward function. Otherwise, if you get, say, too much reward for going right and not enough reward for catching points, the agent will just go right and go straight into an obstacle and die. So that's the situation with the boat going round and round. This is a misspecified reward function where you can actually get more reward just by doing a small loop than by doing the whole race. So you need to have a very good reward function. Yeah.
Is there a way of, we already use something like dynamically reweighing the different uses of the reward function depending on the situation? Like when you get stuck on such a tube, for example, like a water tube, and then there's like something like an inverse learning rate where it says, okay, walking right, I learned this one.
In the general idea, that's actually how we will implement the curiosity of our agent. So we will see in a few minutes. Actually, that's what you need to do, yeah. And so yeah, if you go back to your notebook, your agent that was running, I hope that the training is finished for everybody. And if you run the agent, oh, this is not this one. Yeah, this is this one. So after training the agent, we can run it once again. So yeah, remember our agent was moving randomly because we had not trained the network yet. And now we'll just run 3 games, prepare an animation, and watch in just a few minutes, the duration of the small break we just had, what could our agent learn in that small time frame? So it's going right. It dies pretty quickly. It's not able to play perfectly because, well, we just trained it for like 15 minutes, but it's already something. It's not going left anymore. It jumps over the different adversaries. It jumps over the pipes. Well, yeah. Still needs more training. But if we go further and train it for 4 million steps, this is what you get. So now it's able to finish the level. And again, you can see that the network converged, so the policy, notice that the probability of doing the action we are doing is almost always 1. So the actor is really certain of what the optimal action is right now. and the reward we get is really high. Yeah.
So how variable the conditions are over different runs? Because I mean, maybe the enemies could be in different points, because otherwise you could be overfitting the level, right?
Yeah, that's true. So if every time you run an episode, the enemies are at the same positions and moving at the same speed and everything, your agent will overfit to this particular game. But every time we reset the game, actually there are small random components that are actually not implemented by us, but by the environment itself. So for a given action in a given state, you don't get always the same state back. You get a distribution, there's a probability distribution of different states you could get. Yeah.
How is the distribution for the training time for the RNN? How much training time of one action needed do you require for the CNN to provide enough information for the RNN actions to have something useful?
Well, the internal state of the RNN is detached, so the gradient is cut for the backpropagation after every rollout. So basically, your RNN is trained on batches of 20 steps. I don't know if that answers your question. More or less? Okay, so you can see that the reward is almost always, it's always the maximum one, so you get this high positive component, which is going right, and you can see that periodically the reward drops. This is another component of our reward function that I forgot to talk about. Why do you think we periodically make a small decrease in the reward? How can that help? Every 4 or 5 frames or so, we have a small penalty on the reward. Exactly, to make it faster. So if your agent is finishing the level but takes 500 steps to do it, and if another agent is doing the same level, it's completing it, but in only 50 steps, well, the second one will be better. So yeah, you add a small negative component every time a few steps have occurred.
But is that why it doesn't learn to go in the pipes?
Well, it doesn't go in the pipes always. Sometimes it went in the pipe during the training, yeah. Because you have a secret way to go directly, almost directly from the start of the level to the end of the level in Mario. So if you enter a pipe and go in the cave, you can, go back up again next to the end of the level. It occurred sometime during the training. If you train it for more steps and you have all the material to do that, you could maybe see that it goes more and more often through these pipes. And the final observation is that the value is constantly decreasing, almost always constantly decreasing. And this is because the reward we get is almost always positive. So the critic is always saying, okay, there is less reward to get in the future than before, because we catch some. Is that clear? So for instance, here we are reaching the end of the level. So what are the future rewards we can get from this point? Almost none, because the game will be over. And when the game is over, there's no reward left. And you can see that the value dropped to 0. So the critic understood that when you are at the end of the game, there's no reward left. Now I'll pass the mic back to Axel to introduce you to the concept of curiosity and solve all of these rewards problems by making the agent learn his own reward.
So, as Thibault touched upon during the presentation, until now we have been working with extrinsic motivation. So you receive a reward for all the action you take. And by this, you actually encourage the agent to do the behavior that you wanted to do. But that has a lot of problems. You can't always build the perfect reinforcement, the perfect reward function. So in humans, as I said, you have different motivations. You have motivations that come from the inside. Usually you do stuff that you like to do. Maybe you go to work for your paycheck, or maybe you go to work because you love what you do. And it's good if you do it for both. So in this example, you see this little boy. He's having an extrinsic motivation to play football. He's playing football so he can win the cup and maybe impress his parents. They will be so proud of him. Then you have the intrinsic motivation. The other boy, he's actually just simply enjoying the game. But what does it mean to enjoy something, to have fun when you do something? Research in how children learn has shown, and also apes, has shown that actually when you're learning in general, you actually build rules for the world around you. So you build a model of the world that is around you. And when there's a mismatch between what you expect to see and what really happens, you're actually surprised. And this is something that can be used to put the attention of the agent on that surprise. So in this situation, you're going to see a man performing a magic trick on this ape. Magic trick. He's going to put something in the cup, going to show the ape that he has put something in the cup, then remove, shake the cup, remove the object, and then show it to the ape again. And the ape has this model in which there is something in the cup. And when there's nothing, he's a bit surprised. And actually what happens in here is that the ape finds this interesting. He's going to look again and ask again for the trick, because he wants to understand what happened. And this is something that can be seen also in small children. When you expect something and don't see it happen, this surprises you, and then you put your attention towards it. You try to understand, to reinforce your model in your brain. So don't be scared, it's quite easy. So how do you model surprise? So as I said, you have your conception of the world around you. So this conception of the world around you can be seen as this forward model. This forward model will take as an input the phi function of the state, which is actually the state encoded into this intrinsic curiosity module, which is the big one here, and also takes into account the action that it takes. So it's going to say, okay, I'm throwing this in the air, and it after some time is going to fall down again. If it gets stuck, it's going to be surprising. So this forward model is going to build the next step. So the predicted phi of t of the st plus 1. And you also take as input the next state, so the st plus 1, which is going to be encoded in phi st plus 1. And then you're simply going to take the difference between the prediction and the reality of what happened. And this difference is going to be the intrinsic reward. Does it make sense to you? Yes?
So what is the reward? Is it just a scalar, or?
So it's just going to be the difference between what was expected and what really happened. So then it's going to be just a narrow function. So it depends on the situation what you want to consider as real or not. And then in this first paper by Patak, he's also going to introduce an extrinsic reward. In the implementation that we're going to present to you, there's going to be just the intrinsic reward, so only the curiosity. So this is really interesting, because by just giving this concept of building a model in the head of the agent, and to be surprised when there's something new, it's going to be able to learn on its own without any specific information. So it's not going to have information about the score, about how many enemies there are, or anything. He's simply going to build an image, and whenever there's a surprise, he's going to try to do this again to understand what is going on. And now I let Thibault show you how to code something like this.
Okay, so yeah, let's go back to our notebook, and we have a new class of agent, the curious actor critic agent. So basically we inherit everything from the traditional actor critic agent. We still have this actor producing a policy, the value, evaluating how good the states we are visiting are. But in addition, we built this curiosity module around. So instead of using the extrinsic reward, as Axel said, we will only use the output from this intrinsic curiosity module as a reward signal. So yeah, basically when we initialize the network, we initialize the actor critic network, but in addition, we initialize this new intrinsic curiosity module. Again, for the curious ones, you can go into the code on the networks file of the code to understand how this neural network is implemented. And Another difference that Axel mentioned is that we are not giving any feedback from the environment to our agent. So we don't give the reward, but we also don't even give information about whether the game is over or not. If you look back at the code for the traditional actor-critic agent, when we end the rollout, we have a special condition for when we are in a game over state. We tell it that the value is 0 because there is no more reward to get. Here, we reset the environment to start a new game, but silently, without telling the agent you just lost the game. Because in a sense, telling the agent when the game is over is leaking some information about the goal. It's part of the reward in a sense. It's used to train the critic, and we really want to give no external information to our agent. So yeah, for the agent, a sequence of 100 games would just be a really, really long episode. The training loop is the same as for actor-critic, because the actor taking the decisions and the critic evaluating them are still the same, but it's that get-reward function that changes. So remember that in the traditional actor-critic, our reward is just a clipped version of this extrinsic reward parameter, but here we are not using this extrinsic reward parameter to compute the reward. We will use this observation. So at the end, we need this function to output the intrinsic reward, the curiosity of our agent. Again, we clip it between -1 and 1 to give it in a reasonable range. So by looking at this architecture again, and by inspecting the code from this get-reward function, you will try to implement this intrinsic curiosity module just by finding the right arguments and outputs for these two functions, the forward model and the inverse model, and the two parameters for this function that compute the intrinsic reward. So you can take a few minutes, maybe speak with each other, exchange your ideas of what should go in which network, and yeah, in around 10 minutes we'll see how it goes when we... Okay, so does anybody have a suggestion for what we should give as input to our forward model? Yeah? Yeah, the last features, that's one of the input? That's one of the input? Last action? So your forward model, I mean, the name describes it pretty well. It tries to predict what's going to happen going forward. So you give it the last features. That is, you pass your observation of the environment through a convolutional neural network to extract features about it. So you take that from the previous step. And the last action. And using this information, so basically the last state I was in and the last action I took, the forward model is trying to predict something, right? So what should be this output? Exactly. We are trying to predict the features of our current state. And now for our inverse model, again we have two inputs. So looking back at this image, this is your inverse model. So its two inputs are these two feature vectors. Your features from the current state and your features from the previous state. So basically you will give us two inputs, the last features and the current features. And using that information, what are you trying to predict? The action, yeah, so the last action. So basically the way you're training your inverse model is saying, well, my environment used to look like that, but now my environment looks like that. Guess what action I did in between? So then we need to compute an intrinsic reward, a curiosity. Yeah, sorry. you will compare this predicted action with what was actually your last action. So then to build our intrinsic reward, what do you think we need to compare to get this idea of surprise and curiosity and identify situations where we predicted that our environment would would look like something and get a high curiosity if it ended up being something else? What are the two variables we are trying to compare here? So yeah, you are trying to compare the features you predicted with your forward model and the actual features you just encoded. So now, I just have an interesting question that came up. To compute your curiosity, you're looking basically at the forward model loss. The forward model is trying to predict the features of your next state. And you're using the mean squared error between the features and the predicted features to get this reward signal. The inverse model, its output, the prediction of what the last action was, is not used. So yeah, this inverse model, we store the action, we try to predict what action happened between two consecutive states, but we are never using the output for anything. So yeah, why do we do that? And the idea is that we use it such that our training, our encoding of the environment states contain enough information to understand what are the consequences of an action, and we want only to store this information. So in the original paper introducing this intrinsic curiosity module, they have a good example. So say you are looking at a tree and there's wind. So the leaves of the tree will move a lot. If you're trying to just predict your the actual state in the future, I mean, you will not be able to predict perfectly how each leaf of the tree moved because of the wind. It's very difficult to predict, and most importantly, it's not important for you to accomplish your goal, and you should not be curious about leaves of the tree moving because of wind, you know? So using this inverse model, you're basically telling, well, this feature extraction should be trained to extract elements of the observations that are important to understand my actions. My actions have no influence on the wind in the leaves of the tree, you know? So I don't need to encode, in my features, I don't need to encode this position of the different tree leaves. So I need to focus on elements of the observation that my action can have an influence on. And that is the goal of this inverse model. So we don't use the output of the inverse model, but we simply train it such that when backpropagating to this feature extractor, the features we are extracting about the state, we focus them on what my actions can have as an influence on the world. Is that clear? Okay. But yeah, the question came up multiple times. Yeah.
So the features feed network is only trained by the inverse model, nothing else?
It's trained by the inverse model, but also by the forward model. So you're also trying to extract features that are easy to match and predict from one step to another. So yeah, both the inverse and forward model are backpropagating through the feature extractor. So now we have coded our curious agent, and we will be able to run it. So training a curious agent takes time. I won't show you again the agent without training. We know that it will basically be random, but you can load a checkpoint using this cell of the curious agent trained for 4 million steps. And we will replay what happens when we run it in the environment. will generate 5 different games. You can see, for instance, that this game was really short, the fourth game, so the agent probably died pretty quickly. But the other games, you can see that the value of the reward we obtained is quite high, so that's a good sign. Again, this is not the actual reward from the environment. This is the sum of our intrinsic curiosity. So you cannot compare these reward values to the one you have for the traditional actor critic. So let's see what happens. Remember, this agent had no information about what the goal of the game is, no extrinsic reward, no signal about when the game is over, and it basically learns also an optimal strategy. It goes right, avoids obstacles, jumps over pipes and holes, not always. Yeah, so you can watch the agent, and let's see in video what happens inside our neural network. So, yeah, without training, it's random.
All right, guys.
As we go to 1 million step, you can see that you already get peaks in the reward function.
So the first group that we invite to come here and present their method, the result, is the Swiss Army knife.
So here, for instance, you have a peak because the agent was in that situation, and it ended up in that situation. And it was surprising to him, because its environment changed completely. The features about the observation, the frames of the game, it was really hard to predict that in this situation, when you go, I don't know the action it took, but basically in this situation, it's really difficult to predict that you're going to end up in this situation. Because the agent has not learned yet what death is, basically. So it's surprised by death, and as we don't give a death signal, it's trying to do it again to understand it more. So it's, yeah. And you can see that the probability on the right, in the policy, so that the probability for actions going left are really low. So our agent is still discovering and learning how to solve the level. So why does this work? Because Mario is just a linear race. You know, you have to go as right as possible to discover new situations and new states. And every time the agent goes somewhere on the right it has never reached before, it will be really surprising to him. So here, at this step of the training, after 2 million steps, the reward is really low. Maybe that's because for stability purposes, remember that our reward now is the loss of the forward model. So basically it's changing through time. We are in an environment where the reward function is not constant. There's no stationarity. So to stabilize the training, we are dividing the reward by a running mean of its standard deviation. So basically when the reward signal is really noisy, we divide it by a large value to bring it towards 0 to prevent random updates. This is an important part for stabilizing the system, because what you're doing is actually some kind of, once again, adversarial training, because you train your forward model to minimize the curiosity. The curiosity is the loss of the forward model. You train your forward model to be good at predicting the next states, so you're training for a low curiosity. But the actor critic is using the curiosity as a reward, so it's trying to maximize the curiosity. That's why the training can be quite unstable and is slower than without the intrinsic reward. But still, without providing any information about the game, we are able to go far. And yeah, I can go forward. What's happening here is quite interesting. You see that the value is growing because the agent is close to somewhere in the level where it will get a lot of reward. It will be really curious because it's a place it has not explored a lot until now. So it's still a region of the environment where it's difficult to predict the next features. You can see that the reward is going up. And now, here, you see the drop in the value function. That's because usually, when you're in that state, you end up dying. I mean, that's what the critic tells us. The critic is telling us, in general, when I'm in this state, well, the future rewards I can get are lower. But when it finally reaches the other end of that hole, the critic value is jumping. It's going right up. Because now that the hole is behind us, there is no risk to fall in it anymore. And usually from this state, we are getting a lot of rewards. But then we die, and we end up back again at the start of the level. And I mean, we've been training this for 4 million steps. So the first frame of the game, that starting point, your agent has seen this a lot. So the forward model had a lot of training iterations on these observations. So basically, after 4 million steps, the agent is not surprised anymore by the situation where the game starts. And it's not curious anymore about the start of the game. So he wants to go right, to go back to that place where he doesn't understand what's happening yet. That's why making Mario curious was sufficient to make it learn how to play.
So now, so as we said, in the case of Super Mario, it is quite interesting. I would like you to think for 5 to 10 minutes about the benefits of using only the intrinsic curiosity to perform the task. If you see some problems in this approach, so let's say, is it possible to hack the intrinsic motivation, as we have seen with the boat, for example, and how you would solve these problems by the problem being if you use intrinsic motivation to train a reinforcement learning agent. So first point, you don't need to build a reward function. As we have said during the presentation and during the coding session, for a lot of environments, so in the case, for example, of Super Mario, it's really engineered to be the most perfect possible, this reward function. But in a sense, this is constraining the use of reinforcement learning, because you really need to apply, to use this reward function only specifically for Super Mario. You can't use this into a new environment. And thus, when you start to work in another game or another application, you need to really, again, hard code this reward function. And then at the same time, you can also have situations in which this hard-coded function is not good enough or is not bringing you the optimal policy. Do you have other ideas?
Uncertain environment.
Uncertain environment. So by uncertain environment, what do you mean?
You don't know all the, you don't know have perfect knowledge to actually code the function, so not perfect knowledge yet.
Yeah. Yeah. So it's not. So yeah. So your point is really good. So if you want to build this perfect reward function, you need to know everything. And maybe in a game you can know everything, but in real life you can't know everything. And this is really important if we want to apply these reinforcement learning techniques towards real life. Yeah. So highly repetitive levels. So this is also a really good point, in the sense that your agent is actually overfitting for that level. In the case of intrinsic curiosity, it's going to have another aspect towards this. Maybe it's going to overfit towards that level, but if you put it in another level, it's going to learn in a different manner, because he's going to learn when there is something new appearing, or when he's stuck somewhere, he's going to try something else. So he said, as we I think it was you who pointed this out before, this reward function is static in the case of standard reinforcement learning. In the case of intrinsic motivation, this reward function is going to vary, and it can go from exploitation to exploration. If, for example, he's in a situation where it's always the same, he's going to go back towards exploration to try to find new policies. Yeah.
Maybe a benefit is that you're not getting stuck in loops because of extrinsic reward.
Yeah, so not getting stuck in loop because of extrinsic rewards. Yeah, again, so it's going to be this trade-off between exploitation and exploration. But at some point, yeah, as we saw, and you're going to see a few examples later with Thibault. For example, if you apply your model from the level 1 to the level 2 in Super Mario 1, you can't get stuck. Well, you'll see the situation, but to get stuck out of a situation, you need to go back down, and then you can go back to the right. For the standard reinforcement learning, he just learned to go to the right, and that's it. And the policy will always be to the right. In the case of a curious model, it's going to still have a little bit of probability to go to the left. And you'll see through the examples that it is possible for this curious agent to get himself out of a stuck situation without needing to train him for too long. Do you have other ideas? Yeah. Sorry? So what you're saying is if the game is too boring, the curious agent will just not be interested in this area and try to get out of that situation. Yeah, that's also correct. So as Thibault said, in the case of Super Mario, this is something really interesting because in Mario you need to go to the right to discover new things, to discover the new environment. So for this case, it's really good to have this curious agent. But there could be also some situations in which being boring is something that is good because you don't want to see new things, you want to start to exploit the situation. Yeah. Other points or? Okay.
We list any benefits, huge benefits of this?
Yeah, so the other benefit is the fact that you have this reward that is actually not sparse. So in a sense, for example, when we were talking about breakout or Pong, you only get 1 point or lose 1 point in really rare situations. By having actually a curious model, it's going to try to find new exciting things to find out. And this reward will not be linked directly towards getting points or losing points. And this is really interesting because by having this curious aspect, it could be applied to real-world problem where the sparsity of rewards is one of the big problems.
So you have all these benefits summed up in this slide. And someone asked me, we will put the slides on the GitHub repository at the end of the workshop if you want to download them. We talked a little bit about training in one environment or in a simulation and then deploy and test in another environment. And that's something you do quite often in reinforcement learning. For instance, if you want to pilot planes, you don't want to do hundreds of plane crashes before you know how to do it. So even for humans, we do that. Humans learn to pilot in simulators. So a way to simulate kind of the same situation for our Mario agent is to train it in the level 1 of Super Mario Bros., which will be our simulation. But then what we really want, our ultimate task, is the agent to be good in the level 2. Because no simulation is perfect, so there will always be a difference between one environment and another, and you need your agent to adapt to that. So if you go back to the code, we have these checkpoints for the agents trained on level 1. So we will create these agents, one not curious and one curious. But when we call the play function, instead of calling Mario level 1, we will call Mario level 2. Here I activated the train parameter. So when you run this code, the agent will start to be trained on observation from level 2. If you want the code to run faster, you can just replace this parameter to false, such that no backpropagation will be done, and you will just see, as it is after 4 million steps on level 1, what are the performances on level 2. And in the meantime, I can show you a video, because in case you don't have to train it before the end of the workshop, you can see what happens. So this is the traditional Mario, trained on 4 million steps on level 1, and this is what happens when we launch it on level 2. You can see that it preserved quite a good knowledge of what a good policy is. It goes right, jumps over obstacles, but oh, oops. The problem here is that our agent learned that going right is a good stuff, and there's no, as Axel mentioned, there's no situation in the level 1 where you would have a pipe or something you need to jump over. You can always get to the other side. Here it's a new situation that only occurs in level 2. You have an obstacle, you can jump over it, but it's a dead end. And as our agent learned to go right, it's stuck in the dead end. And it's getting almost 0 reward, so we have almost no feedback anymore about what our actions are. So to get out of this dead end, you will actually have to wait for the end of the episode. I'll just go faster, yeah. So here you have the time displayed on the frame. The agent will never get out, and we wait until the time is 0, the game is lost, and we start a new episode. And you will see that, yeah, the environment is changing quite a bit from one game to another, so we will not always get stuck in this dead end. We are still able to jump over obstacles and everything. And our agent is often losing at this very difficult passage from the level, because you have this enemy coming forward you, but the passage is really small, so most of the time you will die at this point. So now, we could say that the knowledge from the first level is still transferred pretty good, and let's see what happens if we use our curious agent to do this transfer. It's getting stuck again, so... Okay, so this is the curious one. At first, yeah, it seems that it's not that good. But sometimes, it is still able to go right, kill enemies, and here it's doing something that we never saw our traditional reinforcement learning agent do. When it's jumping over the turtle, it sends it to kill the enemy on the other side of that difficult passage. And now it's clear and it can go. And you can see in the reward function, our curiosity, that the moment where we do that, the reward function is jumping. So you would usually get a reward of below 0.5, I say. And then when you do that, you are really curious about what's happening. Some really weird stuff are happening in your environment, like all these enemies dying alone. So you get +1 rewards at some point. We have also a situation where the agent is stuck. So let's see how it goes. So it's stuck, okay. It can happen, but it can go left. And that's a good thing. It's still curious. The policy hasn't converged totally yet to one probability on one action. So sometimes the agent decides to go left. It still explores a little bit, and that's a good thing, because that's the only way we can get out of our dead end. And when we do, well, sometimes we are, yeah, this is just a really weird part of the environment for the agent, because it doesn't look at all like level 1. So sometimes it still wants to go back in. But as you said, at some point, this part of the environment, which is now completely new, will be really, really boring. So it will stop going. So, yeah, I just splitting that a little. Will it get out? Suspense. And it did. And again, you can see that in the value function and in the reward function. Let me rewind it a little bit. Yeah. So at the moment where it gets out, look at the value function on the reward function. And it's not a reward generated by the game. It's just the agent that understood, oh, now I'm out of this dead end, so I can see new stuff again, stuff that will surprise me. And when it dies, the value goes back down again. So that's how you can transfer it from one environment to another. It has also already seen the part behind it, but in this case, we continue training in level 2 for 300,000 steps, and we have pre-trained on the first level for 4 million steps. So, okay, it has already seen what's behind him, but relatively to all the data it has seen until now, it's still relatively new. You know, even stuff on the left is new because all he knows is level 1 by now. Yeah. Yeah. So this is the advantage of using curiosity, but now Axel will talk to you about some problems that can occur with curiosity.
Okay, so as we said, using curiosity is quite interesting because you don't need a reward function, but there could be a situation in which being curious is bad. So let's say you're back home, you don't know what to watch on TV, and you start to look at the TV, and you start just pressing the button, and there's something new appearing every time you press the button. And this is interesting because whenever you press a button, you see something else. And then someone comes in the room, looks at you, and you're a potato couch. This is actually a problem that we can also see in intrinsic motivation models. In this situation, the task of the agent was to explore a labyrinth. But whenever he got close to this screen, he was actually given a remote that whenever he would press the button, would actually allow him to change the channel. And since he's not able to predict what is going to happen because it's going to press it randomly, you're going to have this agent just continuously pressing on this button and watching TV all day. And as we were discussing this with Thibault, and if there are some of you who know about randomness in computer systems, it's not possible to have something random. You could imagine that if this agent is actually looking at this for million or billion of years, he's going to find a random seed and able to predict what is going to happen. So maybe after a billion of simulations, he's going to be able to quit looking at the TV and start exploring again.
So I really hope you enjoyed it.
That is one greatest use for binge watching Netflix.
Yes, you could use agents to see if people can watch more TV. And this is the problem of using the surprise as a proxy for training reinforcement learning agents. And actually there's a research group, I think they're from Google? Yeah, from Google, who actually tried to solve this in another way. Instead of trying to predict what is going to happen next, they're going to look at how long it would take to be in the next state. So here you have the observations in memory. So what is going to happen is you're in a specific state, and you know that from this point, so the one in the middle here, you're going to have to do just one step to get to this one, just one step to get to this one, just one to this one, just one to this one. And this is something that is not interesting for you because this is not something that is hard to do. In this situation, for example, for the couch potato problem, the fact of pressing the button will give you something that is just at one step from the state in which you are right now. Then you have the reachable from memory. So it's something that you need to do a bit more steps to do. So let's say you want to be in a different state from where you are right now. How much effort do you need to do this? How much effort would it be for you to don't watch a TV show here, but to watch it in another room? Maybe that is something more interesting. So you would need to get up, go in the other room and watch something else. So this is already something a bit more interesting in the sense of the agent. And let's say you want to watch TV in Paris. So this is way more work. So you need to get the tram, then the train, and then you have to go through the yellow vests, and then you will maybe be able to watch the TV in this other location. And by giving more weight to these in the future states that are more complicated to get to, you're able to bypass this curiosity problem of the couch potato. Does it make sense? Yep. Ah. Okay. So, thank you very much. Just a few takeaways for today. Reinforcement learning has a certain aspect of creativity. So as we said, in a lot of optimization problems or finding the best path possible, you give them an objective and it's going to find the best way possible to attain that objective. And sometimes it is in a ways that humans can't really think about because we are quite limited in how much information we can take in. The machines are not, and this is something that is able then to learn from its own. But it requires rewards and a reward function. So as we said, in simulated environments where we know everything, this is something that can be done. But if we want to apply this in real world or sparse reward problems, it's a bit harder. And the curious reinforcement learning is a possibility to solve the problem. But of course, don't binge watch and do something else from your life than just watching Netflix. Thank you very much. Sorry?
Can you put some of the relevant papers in the GitHub, or at least the pointers to the papers?
Yeah, we'll add them to the GitHub, and every time when we talk about one of they're in the slides anyways, but we will put the complete list, so you can get access to them.